Okay, do we know how to graph?
Just a little.
Just a little? Don't you say that. I know you know how to graph. How do we graph normally?
Dots.
Okay, how do you find the dots?
Coordinates.
Yeah, you find your x and y coordinates, right? Find some points. Hopefully draw a nice graph that looks like a graph, right? So yeah, we're going to be doing some of that here. So obviously, if you're drawing a straight line, you just need 2 points, right? I mean, how hard can that be? Well, it can be hard. I just graded statistics exam, and I was like, oh my God, these people cannot graph. So it looks harder. Well, I don't know. Maybe it looks easier than it is. I don't know. One of those. Circle, and you guys did this in your exam, right? You had to find the radius and the center of the circle, and you've got your circle. But you know, once we start getting into these other, excuse me, graphs, sometimes it cannot be just that simple, right? 2 points or a center and a radius. So that's why you'll see I'm giving you this little T table here, so we can find a couple different points so that, you know, we can get a nice smooth curve or whatever the shape of our graph will be. So usually what I suggest is start with some simple values for x. And normally, and you'll see this in the different examples we do here, I will try to use 0, +1, -1, +2, -2, so that I'm getting both positive and negative sides, and then usually we can kind of see what's happening at 0. Now, some equations this will work, and then some equations these numbers will not work. But you know, these 5 basic x values is always a good starting point. When in doubt, start with these and then see, do we need to expand more points? Do we need to bring in more value? So with this square function that we're looking at, that's exactly where we're going to start. So I'm actually going to use -2, -1, 0, 1, and 2 for my x values. And basically the idea is once we select our x values, you're going to substitute that for x in your equation, right? For x squared, and then find out what your y values are going to be. So when I do square on -2, what do I get? +4, yeah. So this guy is +4. -1 squared. -1 times -1. Right? Yeah, so it's, I'm telling you, it looks like it should be easy. +1, 0 squared? 0, very good. And then again, +1 squared would be 1. And +2 squared. Alrighty, so there you go. Hopefully. Go ahead.
Just for 0, 0. So is that like the...
So I'm just going to write these as ordered pairs. Yeah, so it will be at 0, 0, right? We did get that as our point. So you'll have origin.
That would be the origin?
Yeah. Because remember, that's where our 2 axes meet, right?
Right.
So yeah, it's the origin
But
for
like
the
highest point on a parabola.
Oh, that's what you're talking about. That's the vertex.
Ah.
Yeah. Which in this case, is it going to be the highest point or the lowest point?
Lowest.
Yeah, in this case, yeah, but it's called vertex. Very nice.
I thought it was called the hypotenuse. What's the hypotenuse?
That's like triangle.
Hypotenuse?
Yeah.
Oh, that's the thank you. The line across from the 90-degree angle. Yeah.
Oh, okay. That's the longest.
The longest side of a right triangle. Yeah, very nice. All right, so we've got +1, +1, +2, +4, -1, +1, and then -2, +4. So those should be your 5 points that we just calculated, and then you're drawing apparently as smooth of a curve as you can. And this is your square function, y = x squared. And as Jacob mentioned, this is a parabola, and then the lowest point, since this is a parabola that opens up, the lowest point is at 0, 0 at the origin, which is what we call the vertex of the parabola, but we'll actually be talking about that here in the next couple sections. So like I said, this is not a straight line, so we cannot just do 2 points. So we try to do as many and try to find enough points on the left side and the right side with positive and negative x values to see what kind of shape you're going to get. Now they are also asking us what the domain and range of the functions is, and is it a function? So let's start with, is it a function? Yeah, it'll pass the vertical line test, right? If you draw a vertical line through that. So this is definitely a function. Okay, so we haven't talked about domain and range.
Well, your domain would be all of your x values, and then your range would be all your y values.
Very nice. Okay, so with this function, what do you think all of our x values possibly can be?
-2, -1, or it would be negative infinity, infinity. There you go.
Very nice. All real numbers, right? Because think about this. The idea is, and you can't really see, there should be an arrow here. But the idea is these arms obviously just keep going up, right? Because obviously it's going to keep extending, which means as it goes up, this arm will also start getting wider on both sides. So the idea is that it's actually going to cover all the x values on your x-axis, which means it will go any number from negative infinity to positive infinity. Yeah, so it's all real numbers.
No, why would it be half as much?
Say that again?
Why would it be half as much? Because
Okay.
you
So
shouldn't have two
what do you
repeating
mean?
numbers. Like 1, 1, 4.
So the y values would be repeating. Is that what you're
Yeah.
saying? Yeah, they would be. But then how would you write in interval notation your range? Because what values are we not using on the y-axis? Yeah, we're not using negative. So how would you write it?
Bracket 0.
Okay.
Bracket 0.
Yeah, very nice. So even though we don't have any negatives, and you can see that on your graph, right? Because we don't have the graph below 0, 0. This part is all blank. So that means on the y values, you're actually starting at 0. And again, since our arms are going up, you will be going towards positive infinity. So yeah, very nice, Levi. So your range is going to be bracket from 0, because we are including 0, and then going to positive infinity as far positive as it'll go, right? Okay, anybody questions on those parts? Because remember how I was telling you last time, with domain and range, it's going to keep popping up for all the different types of examples we're going to be covering in this course. Everybody okay so far?
It's good so far.
Okay, that's good.
Unless it gets harder.
Well, you do have to throw a few curveballs at you. Okay, so now we're going from the square to the square root function, and we had actually talked about what kind of restrictions do we have on a square root? What kind of restrictions are on a square root?
Yeah, it can't be negative.
It cannot be negative, so what can it be?
Positive.
And? If it's I, then you're going into the negative.
Oh,
yeah. So it can be positive, but one more number. Yeah.
0.
So square roots can be 0 or they can be positive. So that means your x value can be 0 or it can be a positive value, right? The moment I put a negative x in there, I'm looking at imaginary numbers, I. So we don't want negative. So I actually cannot use the same -2, -1, 0, 1, and 2 here like we did for our square function. So x can be 0, x can be 1. What would be the next happy number for x in this case? Yeah, 4. Because 4 is a perfect square. And I need one more. It's okay. Iron's sitting there and doing finger counting for me. Okay, so we're taking 0, 1, 4, and 9. Because remember, since your x is inside the square root can be positive or greater than 0. So what is square root of 0? Okay, square root of 1, square root of 4, and square root of 9. Alrighty, there you go. We've got our points to draw our graph. What kind of shape will that be?
Kind of a funky parabola thing.
Yeah, it's actually going to be a parabola, but Jacob thinks it's going to be a funky parabola. Very nice, yeah. Go ahead. Yeah, because you're not going to have negative sides on it, right? So you're going to be starting at 0, 0, 1, 1, and then you are positive 4, positive 2, positive 9, positive 3, right? So this is actually going to be just the upper arm of a parabola that's opening to the right. That should actually look more like a smooth curve instead of whatever this thing is. Okay, so who would like to tell me if this is a function or not?
A function.
It is. It will pass the vertical line test. It is a function. Okay, domain? Yeah, because again, remember, x can only go from 0 to positive values. We cannot have negative numbers in here. So your domain is actually going to, again, go from bracket 0 to infinity. And you can kind of see that on the graph, because you can see, again, we're not using any of the x values on the negative side. We're starting at 0, and our graph is going to go up to the right. Range? Name, yeah, because again, there's no graph on the negative side, right? We're just starting at 0, and the graph would be going up. So in this case, your domain and range are actually going to be the same interval notation. Did anybody have questions on this guy? No, it wouldn't be a complete parabola, because think about it. If it was a parabola, then you would have this side, right? And it wouldn't pass the vertical line test. So yeah, this guy actually fails if you have the complete parabola. Very nice. Yeah. Any other questions, comments? Okay, what do we got next? Okay, so this one is talking about a parabola opening to the right. So you will notice if you compare this to equation 1, or example 1, we had y equals x squared, right? And it opened up. Number 3 is now x equals y squared. So we're actually changing where that square goes. And good?
It's gonna open to the right, right?
It is going to open to the right. So what I'm actually going to do here is, instead of picking my x value, since we have the y square, I'm actually going to be using those same points, -2, -1, 0, 1, and 2 for y, and then plug that in to calculate x. So we're just reversing our process here, and that's only because the square is now on the y term. So what are those x values going to be?
4, 1, 0, 1.
Yep. Because now the y values are getting squared. Okay, so this graph is going to be again at 0, 0. You've got 4, -2, 4, +2, 1, -1, and 1, +1, right? So then this is your x equals y squared. Can we call this guy a function? No. No, because he's going to fail the vertical line test, because if I draw a vertical line through this graph, it crosses at 2 points, so it's actually not a function. Okay. Domain. So if you're saying -infinity, that means we should have graph on this side also, right, for the domain? This domain is the x values, yeah. So how would you write it? To infinity, right? Yeah, because again, you're starting at 0, 0, right? We have no graph on the negative side. Because in this case, what's happening, since you are doing the y square, square is going to make everything positive, right? Which means your x value will actually never be negative for this example. And so you will actually be starting at 0 and going to positive infinity, because again, look at that graph. You start at 0 and you're just going to the right. Now, what can you say about the range for this relation? Because it's not a function.
Negative infinity.
Yeah, because what's happening here is this arm, as it goes to the right, will also go down, which means he's going to go towards negative infinity. And this arm will, of course, go up to positive infinity. So if you compare this with example 1, what happened with our domain and range? Yeah, they switched places, didn't they? The domain and range are now the opposite values from that first function, and that's again because this is a parabola opening on the right. Additionally, what I'd like you guys to see, and let me do that here, I've got x equals y squared as my function, right? So if I actually take a square root on both sides, remember with square root we get one positive, one negative root. The square and square root will cancel out, giving you y, and you will get y equals positive or negative square root of x. So what's happening here is this upper arm, well, is the same thing what we did here. So the upper arm is actually your y equals positive square root of x, and that would make our lower arm what? Yeah, this would actually become the negative square root of x. So if you look at these individually, they are functions, right? So if I ignore that bottom half, then it is a function. If I ignore the top half, then that is a function. But if I leave it together like we did with example 3, it's not a function. So if you remember when we had talked about, oh Lordy. No, when we had looked at circles, it was the same thing, right? Because again, you were crossing the graph at 2 points, but you will actually look at semicircles next. I think in the next couple examples here. All right, so we've looked at parabolas opening up, parabolas opening to the right, which it would be the same thing if your parabola was opening to the left, right? Because you still wouldn't have a function. And we've looked at the square root function. Now, cube root. For a cube root, do we have similar restrictions like we have for a square root, where we cannot have negative for x?
No.
No? What's cube root of negative 1? Negative 1, yeah. Cube root of negative 27? Negative 3. So you put a negative in, you get a negative out. You put a positive in, you get a positive out with cube roots. But square roots, or remember we had talked about how all even roots do this, so 4th root, 6th root will all have those restrictions. But cube root, 5th root, 7th root, all the odd ones, put positive in, you get positive out, put negative in, you get negative out. So any suggestions on what my x values can be? I'd probably still throw in a 0 somewhere in there. Negative 1, positive 1, can I use those? Yeah, we'll get nice clean answers. Now think for the next number, which would be a perfect cube so that you get non-decimal answers. 8. And then you can use its counterpart, negative 8, right? Okay. So what is cube root of negative 8? Negative 2. So the idea is if I take negative 2 times negative 2 times negative 2, that should give me negative 8, right? So the cube root of negative 8 is negative 2. So cube root of positive 8 will be positive 2, yeah. Cube root of negative 1, negative 1. So cube root of positive 1 will be positive 1. Cube root of 0 will be 0. And again, remember guys, if you're not comfortable, plug these numbers into your calculator and you'll still get the answers. Just don't use any x value which gives you a fraction or a decimal, because those become hard to graph. So let's see, we still have 0, 0. I've got positive 1, positive 1, positive 8, positive 2, -1, -1, -8, -2. So what will this shape look like?
Now they're called
Oh, we can do better than lines. Squigglies.
I thought it was units, probably.
I don't know, is it white? I'm not sure, I'll have to look that up. I'll take a squiggly for now, though, better than a line. Or an S-ish shape, right? Now, is this guy a function?
Yes.
Yeah, he passes the vertical line test. He is a function. Okay, somebody who has not answered. Christian Torres. What do you think the domain should be for this guy, for the x values? So look at the direction the arms of your function is going in. Very nice, yeah, because like I said, look at the direction of your arms. One is going towards positive infinity, one is going towards negative on the x-axis. Very good. You want to try the range? Yeah, even though they're going to have a slower growth, the idea is this arm will still go up as it goes to the right, and this arm will still go down as it goes to the left. So domain and range will be again same, negative to positive infinity, right?
Or parentheses, so brackets.
Parentheses. For infinity, always, yeah, very good. Always by default. Okay. Are we okay on this graph? Any questions on him?
What's the name of it? Not a squiggly.
No, I know.
I call it the cube root function.
Yeah.
Sorry. Yeah, I don't know. I mean, Alexander mentioned the helix, but I'm not sure. I have to actually go refresh my memory what a helix looks like, so I don't know. But normally when you say any shape like this, we just call it the cube root function. We're not very creative. Mathematicians, you know, we don't spend time on good names. We just call it what it looks like. But I mean, we can, you know, maybe Google it. Google tells you everything. Okay, so this is kind of what I was hinting towards. So if you look at a circle, obviously by itself, a circle is your not function, right? Because it's going to fail the vertical line test. But just like we were looking at the square root of x and negative square root of x, if we just look at the top semicircle, which is actually going to be this equation right here, you have a function. If you're ignoring the top and just looking at the bottom, you've got your bottom semicircle, which is also a function. And you will notice the top one again is the positive square root. The bottom one is the negative square root. So it kind of follows that same concept that your square root of x and negative square root of x has, but this time we're looking at circles or semicircles instead of the square root function. So this actually shows you how we came up with that top and bottom equations. So by default, like we have here, if your circle is centered at 0, 0 and you have a radius r, then by default our equation is going to be x squared plus y squared equals r squared. And normally when we're defining functions, we try to get y by itself, move everything else to the other side. So that's why we're starting out by subtracting the x squared first. So these guys will cancel out. You'll end up with just the y squared from here, and then r squared minus x squared. To get rid of the square, we take square roots on both sides, and that gives us the positive or negative root. So the positive will become the top semicircle, the negative will become the bottom semicircle. Okay, so that's why I've included that little calculation in there. So, you know, with semicircles, when we're doing these kind of examples, we always go with centered at 0, 0. I don't think you're going to see any example which is not centered at 0, 0, because, you know, when we did circles in chapter 1, we had center at 0, 0, we had center somewhere else. For semicircles, we normally try to just keep them at 0, 0. Now, if you get into more advanced classes, of course, they'll change that on us. So the idea here is the first number is actually going to be representing your radius squared. That means we should be able to find the radius looking at this number. And then since this is only going to be x squared, that means you're at 0, 0 as your center. So all you have to do is take the center, take the square root of this number, and you've got your radius, and then you can draw your semicircle. So for a circle or semicircle, we need to know the center and we need to know the radius, 2 things, okay? Like I said, for semicircles, we're already assuming they are at center 0, 0. So all you need is that radius, which will be square root of 16, which will be 4. And then when you're graphing this, center 0, 0, and then go out 4. But now the question is this guy a top or a bottom semicircle? Very nice. Yeah, you have a negative in front of the square root. So this guy is a bottom semicircle. Identify your radius. And then the positive or negative, well, positive, we don't really put the sign, but if you see a negative there, you know it's a bottom semicircle. So from 0, 0, I'm going out, counting 4, bottom, to the right, to the left. So the only one you don't put is the top, right? And then make it look like a circle. Ish. Do not laugh. Hey, that looks like a circle. Yeah, and some of you did really well. You tried really hard to make it look circular. Some, as long as you didn't really give me like corners, you were fine. If you gave me corners, you were in trouble. All right.
I might invest in a compass.
Invest in a compass. But sometimes I give you a radius of 1. It's really hard to get. Okay, dazzle me, people. What will be the domain and range for this semicircle? Oh my God, first time in me teaching this class that has happened where I did not get negative to positive infinity. I am really honestly impressed. Very good.
It's a circle, I guess we're out.
Yeah, because
Not
they don't
extended.
have those arms, right, going to infinity. You don't have arrows pointing in directions like a parabola does. This is going to be confined between just these x values. So you're going from -4 to +4, and we're using everything in between, but that's it. Very nice. So what will be our range then? Hold on a second. So -4 to 4, including, right, your endpoints, and then go ahead.
-4 to 0.
Yeah. So for the, remember interval notation, again, we put the smaller number first and then the larger number. Technically, the -4 here is smaller, and then we're only going to 0 on the y-axis because, again, there's nothing on the top. Very nice. So this will be, as Alexander said, -4 to 0. I am really impressed with both of you. Good job. Extra credit? All right, show me what you guys are going to do with number 6. Yeah, so this is the example I was talking about.
Yeah.
So you know what I do when I graph this? I actually think of my markers being in halves, or some people do it in quarters, so you can draw a little bit of a bigger circle. But if you just want to do in ones, you can. But if not, you can think of this as being half and then 1, or you can do 1/4, 2, 3, 4, and then a 1. So whatever you think will be easier for you to graph. Just make sure it's even all the way through. And then remember, is it a bottom or a top? So you went with quarters? Okay.
Okay. So now.
Did you have a full circle on that other one? Oh, I see. You erased it. Okay. Okay.
Why don't you make it?
So he has to draw a bigger circle.
Use more lead.
Okay, so you shouldn't have a full circle. No, right? Oh, yeah, you can switch to better. All right, what do we got? What's the No, because you have one minus x squared, so because of that minus sign.
I know, it's just 0. Yeah,
No. So what do you have?
0. It's not the whole circle. It's half the
Okay,
circle.
brackets there. Brackets there. Maybe you guys went with the lazy option, didn't you? That's fine. I'm just making fun of you. So yeah, you have radius of 1. I don't do too good when I'm trying to write small things. So I'm actually going to think of these as halves. So I'm actually going to go out 2 units.
So I did better drawing a smaller circle.
You did better? Okay. Yeah, because then you don't have to make your curve that big. So radius is 1. And is this a top or a bottom semicircle? Top, yeah, because it's positive. And radius is 1. So that means we're going out 1, 1, 1. Okay. Brian, you want to tell me the domain for this function?
Does it mean it's the x, right?
The x,
It should be -1 by the positive 1.
Very good. Yeah, so you're imitating the previous example. This one will go from -1 to +1 in brackets. And Justin, you want to try for the range for this function? What would be your y values? Yeah, and again, including those endpoints, you're going from a 0 to, whoa, a +1. So not too far out, right? Questions on this guy? Okay, very good. If we're saying piecewise, what does that mean? It's going to be in pieces, yeah. So what happens with piecewise functions? Because right now, we're saying, like we did the cube root functions, that -infinity to +infinity on the x-axis, it's all going to be the cube root function. But piecewise function actually means you are saying, okay, from x equals -2 to maybe x equals 15. We're going to have this as our function. So it could be an x squared or whatever. But then when I get to x 15 to infinity, I'm actually going to change that square into, I don't know, square root or something. So what happens is over different pieces of your domain, they give you different descriptions of what your function is going to be. So a lot of times you will actually see piecewise functions written in this form where you have your f of x, and then with these brackets here, we're saying for all x values that are 0 or greater than 0, right? Because this is including 0. So we're saying if your x is 0 or a positive number, use x. If your x is a negative number, so if x is, let's say, -5, I'm actually going to put -5 in here, and then -5 times 5 will still end up becoming positive. So your basic piecewise function, you can actually think of the absolute value function, because again, absolute value, remember, is the distance from 0, and distances are always positive, which means our y values always come out to be positive. But if you had to define that function, this is actually how they define the absolute value. So from the positive side, it stays x, but from the negative side, we put a negative in front, so that 2 negatives will end up giving you a positive answer. But before we get into graphing this is kind of what I wanted to show you. So this is what we call as piecewise functions. For this piece, we have a different definition. For this piece here, we have a different definition. So it's going to keep changing. One of the examples where piecewise function happens is actually your shipping example, shipping cost. Because shipping is based on what? And? Weight, yeah. So they're not going to charge you the same price for something which would be like a letter, right? As opposed to I don't know, sending a package or whatever people are sending. I don't know. I don't do packages anymore. I just go to Amazon and say, send it for me. So, whatever they charge you, which I think a lot of us are now, doing more of that online than ourselves going in packaging. Yeah. And so, but think of piecewise function in terms of your shipping cost based on how far it's traveling or what the weight of the package is going to be. Okay, so let's take a look at how we can do these calculations here. So I'm actually going to choose two different values. So let's say if x was positive 5. If x is positive 5, that means you're actually going to be using this piece of the absolute value function. So I would say f of 5 is going to be 5, and my ordered pair would be 5 and 5. But if my x is a negative value, let's say x equals -3, then for -3, I will actually be using the second piece because that's for x equals or x less than 0. So this would actually become then f of -3. I already have a negative sign there in my function. Oh, come on. So negative, which is coming from our function definition, and then x itself is also a negative number. The two negatives give you positive. Your ordered pair here would be -3, +3. So that's actually how the absolute value function works. But a lot of times we don't really define absolute value in this format. We define absolute value with the absolute value symbol. So you can actually use your standard 5 numbers that I normally use, -2, -1, 0, 1, and 2. So take absolute value of each of these. And what will your corresponding y values be? -2 will become +2. -1 is +1. 0 is 0. 1 is 1. So positives stay positives. Negative become positives. 0 stays 0. So what will this graph end up looking like? No. A V, yeah, that's your absolute value shape. So absolute value will actually keep going until you hit that point.
Parabola with straight lines.
So after Brandy impresses me, you're just trying to kill me now. Parabola has to have that curve kind of shape to it, right? I mean, I can see what you're thinking because it still has a little pointy bottom and it's, straight lines instead of a curve, but not a parabola. I would like to live longer. Okay, let me see if I can get that line to go straight. Almost. But yeah, it's that signature V shape of your absolute value function that you should. It will be a function, very nice, because it will pass a vertical line test. Okay, let me see. Can you tell me what you think the domain will be? Great. Domain, the x values. So I heard negative to positive what? 2? No, because it's going to go beyond that, right? Oh. So if it's going to keep continuing, where is it headed? Yeah, so it's going to be, well, now we're back to Jacob's discussion of parabola. It's actually going to be the same domain, right? You're still going from negative to positive infinity because you're going to be covering all the x-axis. Okay. I don't think I've asked you a question officially. What do you think the range for this guy should be? Negative to positive infinity? Do we have graphs on the negative side of our y-axis? So it wouldn't be going to negative infinity then, right? So where are we starting at? Yeah, you're starting at 0, and again, your arms are going up. So you will be going, and let me write this here, from actually including 0 to negative infinity. So domain and range actually does look like a parabola, doesn't it? For the standard form. Okay, so 0 to infinity, including 0 would be the range, but negative to positive infinity would be the domain. And yes, it is a function.
So if I write any parabola on my test, you won't give me a good answer.
I will give you a big fat 0 for that.
Oh.
Because, you know, I mean, it's the question of the shape, right? I mean,
Yeah.
a lot of properties may seem like, okay, this kind of seems to be similar to that, but you still don't really have the shape. Okay. Any questions on that parabola part? Absolute value function. Absolute value. We don't have creative names. Absolute value function. I feel really bad now for mathematicians. We don't have cool names for anything. But we do have a hypotenuse.
When you think about science, kind of just those big words in together.
Well, then, you know, science brings in those Latin names and then game's over. I mean, I can barely say your people's name correctly. So forget about bringing those Latin names in. But yeah, I mean, you know, everybody's kind of taken up. We do more of symbols. So we use a lot of Greek letters and, you know, that kind of thing in math. Okay, so how are we going to go about doing this piecewise function here? Because they are telling us for the first part, you can only use numbers from -2 to 2. Anything outside of that, you won't be able to use this function. But if you're using numbers larger than 2, then you're actually going to be using this portion of your graph. So we're actually going to need 2 tables. I didn't give you guys 2 tables. So we'll draw one. Let's start with that top piece first. And I'm actually going to define for what y value I'm calculating. So for the first piece, this is square root of x plus 2. So your y will equal square root of x plus 2. And these ones are telling us that this is for x values that's including the endpoints of -2 to 2. So you can actually do -2, -1, 0, 1, and 2. They probably will not all give us nice, happy numbers, but we'll at least have an idea of where our points are going. If I plug in these numbers in my square root of x plus 2, what am I going to get? So this guy here, first one, will be square root of -2 plus 2, which will give us what? Yeah, square root of 0, which is 0. For the next one, it's going to be square root of -1 plus 2. Yeah, square root of 1, which will be 1. For this guy, it will be square root of 0 plus 2, which will be square root of 2. And what is square root of 2 approximately? 1.4. Yeah, approximately 1.4. This guy here will be square root of 1 plus 2, which will be square root of 3. And square root of 3 will be approximately 1.7. And then the last one is going to be square root of 2 plus 2, which will be 1. Yeah, because square root of 2 plus 2 will add up to square root of 4. Square root of 4 is going to be 2. Okay. So we've done the first piece of our function. Your ordered pairs are -2, 0 for that first one. So that's going to be on the left-hand side of our graph. Then you've got -1, +1 as your second point. And then this is where we're getting into the approximate. So you've got approximately 1.4. So I'd probably say just a little bit less than halfway, a little bit more than halfway. And those are just guide points. And then we have 2, 2 as a good point to end that. You still have 3 really good points. And then these guys are kind of our approximations. Okay, So remember, this is part of that square root of x function. So you're going to have that parabola shape from just -2 to 2. So you're actually going to have a little of that parabola curve at this part right here. And that's it. It actually stops at +2, right? Because our function for this first part is only going from -2 to 2. Now, once you start using numbers larger than 2, you're going to be using this side of our piecewise function, 4 minus x. So for the second table, this guy will actually equal 4 minus x. Now, here's the thing. This guy says include 2, right, for the first piece. The second piece says greater than 2. So the change is happening right at 2. But greater than 2 can also mean 2.00000000001, right? That minute point right after 2 goes under this guy. So to know if these two pieces actually connect or not, you actually want to start by using 2 in there. Even though we are not including 2 in here, you will still start by that same 2 where the breakoff is happening, because we want to know if those 2 points are going to be connecting or we're going to have to like jump over or something like that. So this point will start at 2, and then you can do 3, 4, 5, 6, whatever you want to use. Because anything greater than 2 is okay. So what does 4 minus 2 give us for that first one? Okay, 4 minus 3, 4 minus 4, 4 minus 5, very good, and 4 minus 6. Okay. This is kind of what I was hoping would happen. So going back to our first piece, the top piece, you see this ordered pair is 2, 2? And then coming to our second piece, that ordered pair is also 2, 2, which means they are connecting. The two pieces are going to be connecting each other. So you are going to be starting right here at the 2, 2 and going to 3, 1. Oh, sorry, wrong direction. 3, 1, 4, 0, 5, -1, 6, -2. So that line is actually going to keep going down. Can I get this on the same screen? Let me see. Oh, almost. So because that first piece is a square root, you get a little bit of that opening parabola right here on this curve. But 4 minus x is actually your mx plus b format with the slope of -1, right? So you are actually looking at a straight line, which that doesn't look like a straight line, but it's a straight line just going down, right? And obviously it's a function. I mean, you can see that it passes the vertical line test. Okay. I think, Amy, I haven't asked you a question yet. So think about your x values, and what do you think the domain for this graph that we have, this function, what is it going to be? Very nice, yeah. So you're going with that arrow on one side, right? So you know he's heading to infinity, which is this right-hand side. So as it goes down, it's also going to the right. So he's headed to positive infinity. But there's no arrow here because that was our starting point, which means we are stopped in a way at -2 on the x-axis. So very nice, Amy. We are going from including -2 on the left-hand side all the way to positive infinity. Does that make sense on the range? I mean domain? Yeah? Okay. I remember. Range for this function.
The range,
Mm-hmm.
it'll be +2 to -2.
Okay, and then in interval notation, how would you write that?
Bracket 2.
No. Smaller value first, right?
-2.
Yeah. So since for interval notation, I mean, your numbers were correct, right? It's just the order. So we put the smaller numbers first. So since you're actually going down, which means you're headed to negative infinity. So the idea is you're actually coming from negative infinity and you're going to stop right here because we don't go above that. So you're actually stopping at that positive 2. So your range is coming from negative infinity and stopping at positive 2. Yeah? So yeah, I mean, piecewise functions, if you haven't had a reason to do that before, you may not have, because piecewise functions can get pretty funky. And again, once you get to calculus, they will do, we're only sticking to, I think, 2, maybe 3 pieces in this class, but they can get, you know, obviously, depending on how far you're going, it can keep changing into multiple pieces. So, you know, what happens is basically the idea is over different values, your function can change. So think about just in terms of a simple economics thing, you know, maybe right now the market is up, right? So you may have a growth pattern, but then your market can stagnate. So maybe you're just staying at that constant level, right? It's not growing, it's not losing anything. But then maybe the market goes down and your value starts losing. So it's going to be from maybe this month to this month, we showed growth, or even in days, I mean, market changes really in days. But then for these days, it stayed about the same. And then on these days, it's falling or growing, whatever. So in that case, your domain is changing, which means what the function was doing will change. So you can kind of think about it that way. Okay? Very good. Any other questions on this guy? All right, so we've got something like that. Again, a 2-piece function in 9. So you're on your own. You've got 4 minutes. Try it. So again, you're going to need, you know, 2 tables. So let's create one for, let's say, x squared. And right, but you know, you want to do the same thing. So even though it's not including negative 1, we want to know if the 2 pieces are going to be touching each other now. So still use negative. Yeah, I would. So what I saw so far, what you guys had definitely looked good. So keep working on that, and then like I said, we'll discuss it in class next time. The graph looks good. Very nice. Graph looks good, Jacob. Are you guys laughing yet? No. Oh, you started. Oh, he was your graph.
Yeah.
Okay. No, the other one there. Were you at the graphing stage yet? The points? Alrighty. Well, we'll pick it up next time then. Sorry?